I wanted to say a few words about something that's potentially confusing, certainly curious, and it concerns the electrical potential or electrical potential difference. The only thing that's physically observable, that's physically measurable regarding the electric potential is the electrical potential difference between 2 points in space. So we can measure, we can observe the electrical potential difference between 2 points in space. On the other hand, the electrical potential at a single point in space, that's not measurable. That's not observable. As an example, you could add an amount of potential to every location in space and not change any physical observable, any physical measurable. So that implies that the potential is ambiguous. You could subtract from everywhere in space a value of the potential, and again, not affect any observable or measurable. Again, the potential itself is ambiguous. What you can observe, what you can measure is potential differences, the electrical potential difference between two locations in space. That's why a voltmeter, a device for measuring potential differences, a voltmeter has two terminals. The voltmeter tells you the potential difference between the two terminals, those 2 points in space. Because you can add or you can subtract a value to the electrical potential everywhere throughout space without affecting observables, without affecting measurements, we can choose a convenient location, a handy location for the potential to be zero. And as long as we're consistent with that choice of where we've chosen the potential to be zero, we'll be okay in our calculation of electrical potential differences. As an example, as an illustration, think about the electrical potential of a point charge when we write down the equation for the electrical potential of a point charge. The equation we usually write for the electrical potential of a point charge is that the electrical potential is K, Coulomb constant, times the charge Q, divided by the distance from the charge. And that's the electrical potential as a function of the distance from the charge. But what we really mean when we write down that equation for the electrical potential is the following. We mean that for the choice of the electrical potential being zero, if you're infinitely far from that electric charge, that the electrical potential at a distance r from that point charge is kq over r. When we write down that equation, we're choosing the electrical potential of that point charge to be zero at an infinite distance from that point charge. Again, really all we can write down is electrical potential differences. We know that the potential difference between distance r from the point charge and infinitely far from the point charge is kq over r. So often it's convenient to have the choice that the electrical potential is zero, infinitely far away from your charge or collection of charges, but it's not always convenient to have the electrical potential zero, infinitely far away from your collection of charges. One example where it's not convenient is if you've got a positive and negative charge plate, and you're interested in the electrical potential in the region of the positive and negative charge plate. Let me make a sketch of a negative and positively charged plate with some separation. And let's imagine that the observable, measurable potential difference between those two plates, the positive and negative plate, is 1 volt. So here's a plate on the left and on the right. I'll make the plate on the left-hand side the negative plate. I'll make the plate on the right-hand side the positive plate. There'll be a potential difference of 1 volt between these two plates. The positive plate on the right will be the higher potential. It's like a potential hill, positive charge. And the negative plate will be the lower potential. It's like a potential valley, the negative charge. And now I could make some choices. So for example, I could decide for convenience that I want to call the left-hand plate 0 volts. And if I do that, it must be because of the 1 volt potential difference that's observable, that's measurable, that the right-hand plate is 1.0 volts, plus 1.0 volts. So that's one choice. Or I could choose to make the right-hand plate 0 volts, in which case, because there's a measurable 1 volt potential difference between the plates, the left-hand plate would be minus 1.0 volts. Or even, if I was a little bit odd or a little bit strange, I could choose to make the plate on the right positive 1.5 volts, in which case, to have the 1 volt difference, potential difference between the plates, I'd have minus 0.5 volts over on the left-hand side. All those choices are perfectly consistent with the observable 1 volt potential difference between the two plates. I cannot measure, I cannot observe. It's ambiguous whether the left-hand plate is 0 volts, minus 1 volt, or minus 0.5 volts, or any other number. Only the difference between the positive and negative plates, the left-hand, right-hand plates, is unambiguous, is a measurable, observable quantity. Anyway, I just wanted to work through that idea, that concept that potential differences are observable, but potentials themselves are not measurable, not observable. And that's an important point about electrical potentials that is quite different from electrical fields.